In this video we're going to look at the integrator. So we've seen this circuit here before. It's the inverting amplifier, so we don't need to bother going in and analysing it in terms of Kirchhoff's current laws. We can really just look back and see what the function was that related the output to the input for this circuit. So if you either go through the derivation yourself in terms of Kirchhoff's current laws, or you could just have a wee look at the inverting amplifier. So in the case of the inverting amplifier, we have the output voltage is going to equal the minus Z2, which is this resistance here or impedance here, and Z1, which is the impedance here. Okay, so but we know that that Z1 is the resistor R. We know that Z2, well, Z2 is a capacitor, and we can write that in the complex frequency, in terms of complex frequency, as 1 upon SC. Okay, so when we put these two in for Z2 and Z1 here, we'll get V out equals minus 1 upon SRC times V in. Okay, so V out then is going to equal minus 1 upon RC. Now 1 upon S is equivalent to, in the time domain, as an integral of the Vi by dt, okay, because the voltage and the input is dependent on the time. Okay, so we're integrating that with respect to time. So that there is the output for this function, which is this little circuit, which is the integral of the input times this factor here, minus 1 upon RC. So about that again in Multisim here, and again you can go and download that and have a wee play with it yourself, and you can check out and see it working. What I've done is I've put a square wave in. So in this instance here, the input is the square wave and the output is the triangular wave, and you can see that the output is the input's been integrated to give us the output, but it's also shifted. Okay, so there's actually an inversion as well. So if we were to, if there hadn't been an inversion, then what we would have had would be what we see here is the input is in blue here, which is a square wave, and we can see that as the area increases here, this line here just increases in a linear fashion as the area under here increases, till eventually the area is a maximum area, and this pink line is at a maximum point. And then again the area is going to start increasing, but in a negative sense here, so eventually it works its way down to its negative point here. So this here pink line is the integral of the square wave there. Okay, so that's all there is to this video, and the next video we'll go on, we'll look at the differentiator. Thank you for listening, and goodbye.